Welcome to Lecture 9. In this lecture, we're going to start looking at how we organize problems to solve them with central forces. It turns out this is a rather technical lecture. We have a bit of complicated algebra we have to work through in a number of different parts in the lecture. There's no simple way of getting through doing this. You just have to slog through it. So I apologize at the beginning that this lecture is going to have some more technical parts to it. So let's go ahead and get started. We're going to consider two particles interacting via potential that only depends on the distance between them. So the Hamiltonian is the kinetic energy of the first particle, P1 squared over 2m1. Kinetic energy of the second particle, P2 squared over 2m2. And then a potential, and the key that we're going to be looking at for central forces is that the potential depends only on the magnitude of the distance between the two particles. So it's a function of the modulus or absolute value of R1 minus R2. Now it turns out that this problem can be mapped onto an effective one particle problem by using what are called average and relative coordinates. Now you probably remember from classical mechanics the definition of the center of mass. I'm going to call it big R. It's given by m1r1 plus m2r2 divided by m1 plus m2. It's a weighted average of the position according to the mass of each particle. Now, because momentum is proportional to each mass, it turns out that the average momentum, which is going to be conjugate to this, is actually just P1 plus P2. And the way that we check is we want to verify that the commutator of the big R with the big P is equal to IH bar. So let's go ahead and calculate that. Let's look at big R alpha, commutator with big P alpha. So big R alpha will be M1 R1 alpha plus M2 R2 alpha divided by M1 plus M2, commutator with P1 beta plus P2 beta. And now we go ahead, and because the one operators commute with the two operators, you can rewrite this. I can pull out the factor of 1 over M1 plus M2. I can pull out a factor of M1 and then have a commutator of R1 alpha with P1 beta. And I can pull out an M2 and have a commutator of R2 alpha with P2 beta. But the commutator of R1 alpha with P1 beta is just IH bar delta alpha beta. And similarly with R2 alpha with P2 beta. So you can see then that I'm going to have the same term IH bar delta alpha beta that I can pull out. And I'm left with a factor of M1 plus M2 over M1 plus M2, which is equal to 1. So the net is that I just get IH bar delta alpha beta. And that's the sign that we have actually figured out these operators correctly, that the average momentum is P1 plus P2. So now on to looking at the relative position. So for the relative position, that's going to be little r. We're going to call that R1 minus R2. And since the momentum is proportional to mass, I have to actually remove the mass. So I have to look at P1 over M1 minus P2 over M2. And then I have to do some razzle-dazzle to put in the right effective mass. And it turns out the right combination is to multiply by M1 M2 over M1 plus M2. That might not be really obvious to you, but if you think about 1 over M1 minus 1 over M2 and think about, or plus 1 over M2, that's actually what this is the inverse of that. All right, but again, the real test of this is to test the commutation relation. So we're going to look at commutator of little r alpha with little p rel beta, and we just plug in the definitions. We group the terms that correspond to the one particle and to the two particle. We can factor out the relevant constants. And then what you see is I'm going to get a net of 1 over M1 plus 1 over M2 times IH bar delta alpha beta. And then this factor out in front, the M1 M2 over M1 plus M2. That's exactly the inverse of 1 over M1 plus 1 over M2. So I get IH bar delta alpha beta. And that tells me again that I've got the relative normalization between these two different objects correct, because I'm getting what's called the canonical commutation relation. Now, in order for this to really be a separation of variables, we need to actually check that the average position commutes with the relative momentum and that the relative position commutes with the average momentum. You can go ahead and easily check that that holds with the definitions that we have done. I'm not going to show that algebra to you separately. All right, now, if we invert the relationships, I can get a relationship for P1 and P2 in terms of the relative momenta. It is ugly, okay? There's no there's no way to soften this. It simply is ugly, okay? And now what we want to do is we want to look at how does the kinetic energy change when I express it in terms of the relative and average momentum. So I have to calculate P1 squared over 2m1 plus P2 squared over 2m2. And this now is a French cooking exercise. It's a lengthy algebraic problem. But all of the operators commute, so I don't have to worry about operator ordering or anything like that. So I just have to plug in and work through it. So when you go through all of that algebra and all the dust settles, and I'll let you pause the video and carefully look at how that algebra works, the key is that the cross terms, you can see those cross terms come in with a plus and a minus sign, and they end up actually canceling each other out. And that then means that I have a term that goes like average momentum squared and a term that goes like relative momentum squared, and then you have to work hard to get the right coefficients. So it turns out we have average momentum squared divided by twice the total mass, m1 plus m2, and then we have relative momentum squared divided by twice the reduced mass, which is that factor that we were using before, m1 m2 over m1 plus m2. And I'm sure you've seen the reduced mass before. So what we find is we've gotten a separation of variables for the kinetic energy. It separates into an average, operators that involve the average terms, and operators that involve the relative terms. Similarly, the potential energy also separates because the potential energy only depends on the relative coordinate because it only depended on R1 minus R2. Okay? That means that we can group our terms together in the Hamiltonian. There's one term that corresponds to the center of mass motion, and because there's no potential that is a function of big R, that center of mass motion is actually the center of mass motion of a free particle. And then I have the relative motion of an effective particle in an effective potential. The potential ends up being the same, but the particle has the reduced mass rather than the mass of either of the particles, m1 or m2. So what we do is we separate this motion into the center of mass and relative motion, and the only change is that we treat the problem as if it's a single particle problem, but we use the reduced mass rather than the mass of either of the particles. And from now on, we're going to drop that relative subscript. We're going to ignore the free particle because free particle is a simple problem. So we're going to ignore that part of the Hamiltonian because we're going to always just add an e to the ik dot big R, and that would add an extra energy of h bar squared k squared over 2m corresponding to the center of mass with 2m1 plus m2 corresponding to the center of mass motion of the system. Okay, now because we're working with central force problems, we're going to have to work with the radial momentum. And I am pretty sure you guys have not had a nice rigorous treatment of the radial momentum because it often isn't done properly in most treatments. So I'm going to carefully go through with you what the radial momentum is. So it's defined in the following way. It's defined as 1/2 the radial unit vector, so R vector operator divided by R scalar operator. So again, R scalar operator is Rx operator squared plus Ry operator squared plus Rz operator squared, square root of the whole thing. That's the scalar radial coordinate. And if I take the R vector operator, which is Rx times unit vector Ex plus Ry times unit vector Ey plus Rz times unit vector Ez, and divide it by R hat, that is a unit vector operator. It's a radial vector operator. But we're going to find that radial vector operator does not commute with the momentum vector operator, P. So whenever you have a situation that you're trying to construct an operator from a classical operator, so radial momentum would be ER dot P, and the operators, the things that you're trying to construct it from, do not commute with each other, then you take a symmetric form because the symmetric form becomes Hermitian. So that's what we're going to do. We're going to take the symmetric form and define that to be the radial momentum. So I take 1/2 R vector over R scalar operator dot P vector plus P vector dot R vector divided by R scalar operator. Now on the homework, you're going to show that the Cartesian momentum coordinates, the commutator with the radial coordinate, R hat, is given by minus I h bar R alpha over r hat. You might know how to derive this in terms of using derivatives, but on the homework, you're actually going to derive it just by using operator relations. We're never going to introduce any derivatives in. And again, this is the way you do things in a representation-independent fashion. And similarly, we're going to show that the commutator of p alpha with 1 over r hat is equal to I h bar r alpha over r cubed. And now that means that we can just plug in, and what I want to do is I want to move all of the r operators to the left-hand side. So in the first term, it's already on the left-hand side. If I move it into the left-hand side, I have to add the commutator of the p alpha with the respective r alpha over r's. And now using the Leibniz product rule, I can evaluate those commutators. The p alpha with the r alpha is going to each give me a minus I h bar, and I have 3 of them. One for the x, one for the y, and one for the z, and then that's multiplied by the 1 over r. And then the commutator of p alpha with the 1 over r, that gives me an I h bar r alpha over r cubed. And that gets multiplied by an r alpha. And now you can see if I sum over the r alpha, I'm going to get r alpha squared. When I sum that over the r alpha, that just becomes r squared. So that gets rid of 2r squareds in the denominator. And I get the same term as the first term. So I'm going to get minus 3 plus 1. That net is then minus 2, but there's a 1/2 in front, so I get a net of minus 1. So the radial momentum is 1 over r hat, r vector operator hat dot p vector operator hat minus I h bar over r hat. And that is the radial momentum. And you can verify by taking the dagger of that it is a Hermitian operator. But it turns out it is not a self-adjoint operator, and I'll have a little bit more to say about that after we go through the canonical commutation relation. So to calculate the canonical commutation relation, I need the commutator of r with pr. So we just write that in terms of substituting in what the pr is. Of course, r commutes with r and 1 over r and so forth. There's only one term that doesn't commute, and it involves an r with a p alpha, and we know what that commutation relation is. You plug it in, and after you do the sum over r, you're going to get an r squared in the numerator, but you have an r squared in the denominator, which cancels, and you're left with I h bar. So again, we think of r hat and pr as being canonically conjugate operators. Now, it turns out that pr is Hermitian, but it is not self-adjoint. And it is actually self-adjointness that is required in order for you to have a complete set of eigenstates. So it turns out the radial momentum has no eigenstates. There are no eigenstates, eigenvalues associated with PR. I cannot expand in a complete set of states of radial momentum eigenstates. It just doesn't exist. Now, how do I know that? Well, that is actually a much more complicated situation, but I will give you a hint about what the difference is between Hermitian and self-adjoint. So you have to delve into the mathematics of Hilbert space theory to really get into the weeds and understand this difference. But it turns out that when I have an operator that acts on kets, the Hermitian conjugate acts on bras. And it turns out that the state of kets that an operator can act on might not be the same as the set of bras that that operator can act on. And the set of operators or states that the operator can act on is called the domain of the operator. In order for an operator to be self-adjoint, the operator must have the same domain for the bras and for the kets. So both the operator and its Hermitian conjugate must have the same domain. When that does not occur, even if the dagger of the operator is equal to the operator, it is called Hermitian, but is not called self-adjoint. And it turns out if you dive into the weeds, and I'm not going to show it to you, in fact, I'm not sure I fully understand all the details myself, but if you dive into the weeds and ask the question about the domains of the radial momentum operator, you discover that that domain is not the same for the adjoint as it is for the operator. So it is not a self-adjoint operator. The reason why we're not diving into the weeds about this is it turns out this does not affect anything that we do. The fact that this operator is not self-adjoint does not affect anything in 1 iota because we never need to expand in an eigenbasis of radial momentum. So that is just a point for you to remember and clarify. This may be the first time that you've heard even the term self-adjoint, and if you had heard it, that you've heard that there can be Hermitian operators that are not self-adjoint, but there really can. And at this stage, the only condition that comes out from this is that there are no eigenstates. All right, so let's go. What we want to do is we want to figure out what is the kinetic energy now expressed in terms of radial momentum. And because we suspect the kinetic energy is going to involve the square of the radial momentum, we're going to go ahead now and calculate it. So this is going to be a tedious exercise because what we want to do is we want to move all of the R operators to the left. So you see what we do is we just write out 2 copies of the radial momentum multiplying each other. And then we're going to use the fact that the commutator of R with PR is equal to IH bar. And now what we're going to do is we're going to show, because the commutator of PR with 1 is equal to 0, we rewrite 1 as R hat over R hat. And then we use the Leibniz rule to separate out a commutator of R with PR and a commutator of 1 over R hat with PR. And then from that, because that total sum is equal to 0, we then can verify that the commutator of 1 over R hat with PR is equal to minus IH bar over R hat squared. All right, so now we just have a commutation relation we got to work out, all right? So I have to move that 1 over R term to the left. I'm going to use the fact that I know what the commutator of PR is with 1 over R in order to work that out. So I move it to the left. So I do an add 0 by adding and subtracting it on the 1 over R factor on the left-hand side, and then that gives me the commutator of the PR with the 1 over R hat. We know what that commutator is. We can then simplify the terms, and what we find is we have then 1 over R squared R dot P times R dot P minus IH bar. I still want to move that R operator in the middle over into the left-hand side, so we're going to write this out in terms of the Cartesian coordinates, and we're going to work out moving that R beta through the P alpha with the Cartesian coordinates. So I only have to worry about the case when the alpha is equal to the beta, where I'm going to get an IH bar, and I only have to worry about that particular commutator. So I get that one term in the middle is the commutator term, and then the last term is coming from the minus IH bar term. So it turns out that those 2 terms are the same. They add together. They give me a 2. And then I'm going to now expand this expression. Okay? So it's just a sum over alpha beta. Remember, alpha is equal to x, y, z. And there's just a lot of terms there. There are 9 terms in that expansion. So we're going to just go ahead and expand all of those terms. And we're going to find we get an rx squared px squared plus ry squared py squared plus rz squared pz squared. And then we get the cross terms 2rx ry px py 2rx rz px pz 2ry rz py pz. And then we get minus this 2IH bar times the inner product between the r and the p. We get rx px plus ry py plus RZ, PZ. And the ordering in that last term is very important. All the R's to the left, just like the ordering in the first set of terms is very important. All the R's to the left of the P's. Now, it turns out that with 20/20 hindsight, we know that the other contribution to the kinetic energy should be the angular momentum. Why? Well, because angular momentum involves the rotational motion. The radial momentum involves motion in the radial direction. The angular momentum must involve the motion that corresponds to the angular rotational motion. So we're going to take a look at R cross P squared. But you do see that in this process of trying to move the R's to the left, which is what, again, we want to do, we are going to encounter things like an Rx with a Px that we have to move through and an Ry with a Py that we have to move through. But it only occurs in a couple of the different terms. We just have to carefully work that through and move it through. I suggest you pause the video and go through and do that. There are 2 commutators you have to evaluate for each of the 3 terms. So there's a sum of 3 commutation relations that you have to add in. Those are the terms on the right-hand side in those 3 lines that are written right below. And now let's take a look at comparing R cross P squared with PR squared. In particular, let's look at the cross terms. So cross terms for PR squared involved Rx, Ry, Px, Py with a plus sign and a 2, a plus sign, and a 1 over R squared. When I look at R cross P squared, you can see that I have a minus 2 times an Rx, Ry, Px, Py, but there's no 1 over R squared. However, if I took that L squared and I divided it by R squared, then those terms would cancel. And you see all of the cross terms will cancel if I look at r squared, if I look at L squared divided by r squared. And then we have to just add together and collect all of those terms from the commutators. And if you look at those terms carefully, you see that those also cancel. They're also gone. So that's kind of a surprise. But I get minus 2i h bar rx px. And if I look at the r cross p squared and divided by the r squared, and if I look at the r cross p squared, you see I have an rx px in the first line and I have an rx px in the second line, and it's plus ih. So there are two of those. So those cancel as well. So it turns out we get this identity, and this is really important identity. Pr squared plus 1 over r squared L operator squared is equal to px squared plus py squared plus pz squared. And then if I divide it by 2 mu, I get that the Hamiltonian is pr squared over 2 mu plus L squared over 2 mu r squared plus v of r. Now, you might not recognize this, but this is the equivalent of taking the Laplacian del squared, writing it out in spherical coordinates, and then recognizing that the angular part is proportional to L squared, which is an exercise that often takes an entire lecture to go through. We did it here in about 5 minutes just by working with the operators. Now, indeed, the algebra is a little messy. We do have a number of lines here. But if you're careful, keep your bookkeeping straight and so forth, you can get through it. And I do think it's a much easier way of doing that derivation. Okay. Now, the last thing we want to work on, it is what I call the radial translation operator. Now, as far as I know, this is actually a new concept. It hasn't actually, I've not seen it in the literature. And I have a paper that I've written on this that I completed about maybe 6-7 months ago. So this is really fresh new stuff that you're seeing here. We want to write the translation operator in terms of spherical coordinates, which involves the radial momentum operator PR, a p theta, and a p phi. Those are not the same as angular momentum, although they are related to them. And we're going to have angular expressions as well that involve cos theta hat, sine theta hat, cos phi hat, sine phi hat. Notice I did not say theta hat and phi hat because the angle operators are not valid operators, but the cosines and sines of them are valid operators. Okay, so there are some subtle points involved in this. This is a place where algebra can get very complicated. So I'm going to not necessarily give you all of the details, but I'm going to give you most of the details as we go through this. Okay, so the first thing to recognize is PR can be written in the Cartesian representation as rxpx plus rypy plus rzpz. Well, it looks a lot like xpx plus ypy plus zpz, but the x, y, and z in the translation operator are numbers, and in the radial momentum, they are operators. So it's not exactly the same thing. However, if we use this identification that rx over r is sine theta hat cos phi hat, and ry over r is sine theta hat sine phi hat, and rz over r is cos theta hat, you see I can re-express this PR entirely in spherical coordinates. And then I can calculate the analogs p theta, which would be e theta operator dotted into p hat, and p phi, which is e phi operator dotted into p hat. You have to carefully work out what these unit vectors are in the theta and phi directions. But when all the dust settles, you find that it is equal to these two expressions. I'm not going to read them out to you. The p theta term has some quantum corrections because it has I h bars in it. The p phi term does not. There's no I h bar terms in it. And you're going to actually go through this algebra in the homework. So you're going to be able to verify this. Now, we're going to use the representation of x in terms of spherical coordinates for the point in space that I'm trying to translate my quantum system to. And we're going to write that as x is r sine theta cos phi, y is r sine theta sine phi, and z is r cos theta. And note here that these are all numbers. The r, the theta, and the phi are numbers here, not operators, because the x, the y, and the z are numbers, not operators. Now, our first strategy is to show that the translation operator can be written as a translation along z, followed by a rotation by theta along the y-axis and a rotation by phi along the z-axis. In many respects, this is the way I go to a particular point r theta phi in spherical coordinates. So let's write down what that is. I know what a translation in the z direction is. It's minus I r over h bar pz. I'm translating by a distance r because I have to translate the whole radial distance in the z direction because I'm going to be rotating. And we're having this act on the origin in position space. So that's x equals 0, y equals 0, z equals 0. That I'm just noting as the ket 0 here. And then we know the rotation operators. We worked them out before. It's like rotating in the North Pole state to the angle theta phi. So I have a e to the minus I phi over h bar lz last, and an e to the minus I theta over h bar ly second, and then the e to the minus I r over h bar pz first. Now, because the origin state, the state at 0, can't be rotated. It's not the North Pole state. It's the state at the origin. There's nothing to rotate. It's just the point at the origin. I can multiply by 1 by multiplying by e to the I theta over h bar ly and e to the minus I phi, e to the plus I phi over h bar lz. You can see I now have two nested Hadamards I've created with regards to the term in the middle. Just to verify, I mean, you can remember that lz is rp, rxpy minus rypx. The r's and p's commute in each component of lz, and an r operator acting on the origin is equal to 0. That's the definition of what the origin is. So you can quickly verify that I can just let those r operators act on the origin. I get 0, and that's it. I'm done. I get 0. So then the exponential of these operators are equal to 1. So now we can just do the Hadamard. Now, e to the minus I theta over h bar ly pz e to the I theta over h bar ly, that's a rotation because the pz is a vector operator. So it becomes equal to sine theta px plus cos theta pz. It's the exact same algebra as we did when we were looking at rotation of vector operators a few lectures ago. And then I have the rotation by the lz. That's going to rotate the px and the py. And since I only have a px in there, I only have to worry about the rotation of the px. That takes it to cos phi px plus sine phi py. And when I plug that in, you see what I get is the translation operator. Okay, you see that is exactly equal to e to the minus I over h bar x px plus y py operator plus z pz operator acting on the origin. So indeed, I have shown that this combination of operators is the translation operator. Okay, as of course physically we knew it must be. Now what I'm going to do is I'm going to replace the pz operator by spherical coordinates. So as we saw before, that involves cos theta pr hat minus sine theta hat p theta hat minus plus I h bar cos theta hat over r hat minus I h bar over r hat cos theta hat. So we're going to plug that into the exponent. This is just plugging into the formula, nothing else. Now, because we're translating along the z-axis, we have effectively that our theta is equal to 0. So cos theta hat acting on this state is equal to the state, and sine theta hat acting on this state is equal to 0. It annihilates the state. So that's a very important thing to remember. Again, we want to remember that PR is given in terms of Cartesians in this fashion, and the commutator of R alpha over r hat with PR can be worked out. It's equal to 0 because, again, that just involves angles. And that means that the PR commutes with cosine theta hat and sine theta hat, as, again, we sort of intimated it does earlier in the lecture. Now, the p theta has this complicated form, cos theta hat cos phi hat px plus sine theta hat sine phi hat py minus sine theta hat pz minus I h bar over 2 cotangent theta hat over r hat. The minus sine phi hat lx plus cos phi hat ly, we can also write that in terms of the spherical coordinates. I'm not going to read that out for you, but you have it down here for you. You might want to carefully work that out for yourself and see what the simplifications are as you get that into the Cartesian coordinates. Okay, so now if I look at sine theta p theta, and work out what that is, that's equal to minus ry lx plus rx ly over r squared minus I h bar over 2r cosine theta hat. That means that if I look at cosine theta pr minus sine theta hat, that should be a hat on that theta, p hat theta plus I h bar over 2r cosine theta hat, that is going to equal cosine theta pr times this ry lx minus rx ly over r squared plus I h bar over r hat cosine theta hat. Let's move the cosine theta hat to the left. Remember that commutes with the pr hat. Let's bring that I h bar over r hat in with the pr hat. We get that this is equal to pr hat plus I h bar over r hat cosine theta hat plus ry lx minus rx ly over r hat squared. I want to move the r's to the right-hand side, but r does not commute with lx. So remember, r is a vector operator. So we can calculate what is the commutator of ry with lx. And it turns out that that is going to give me, when I move the ry past the lx and when I move the minus rx past the ly, in both cases I'm going to pick up a minus I h bar rz over r squared. There are two of those guys. And when we recognize that rz is just equal to r hat cos theta hat, you see I get minus 2. I have a plus 1. So that's going to change that plus I h bar over r hat to a minus I h bar over r hat times the cosine theta. And now I'm going to replace the rx and ry in terms of the sine thetas and the sine and cosines of phi's. And now what I'm going to do is I'm going to re-express the lx and ly in terms of the Cartesian coordinates with the p's and the r's. And that's going to bring out some additional angular operators, because the r operator is divided by r hat. That's going to give me an angular operator. You can carefully go through that and see that you get all of these different terms. And so now when all the dust settles, we get this complicated expression here. PR minus I h bar over r hat cos theta hat minus px cos theta hat sine theta hat cos phi hat minus py cos theta hat sine phi hat plus pz sine squared theta hat. When this acts on the origin state, because that's what it's going to be acting on in an exponential, all of the terms with sine theta hats, they go to 0. Because I'm doing this, if you like, you can think of this as infinitesimally translating along the z-axis, and the cos theta hat goes to 1. So all of the terms that have sine theta hats disappear, and the cos theta hat can be replaced by 1. So this acts like p hat r minus I h bar divided by r hat. And because these angle operators commute with the PR operators, when I raise this to any power, it gives PR minus I h bar over r hat raised to the power. This is the reason why we had to move all of those r hat operators to the right-hand side so that we could get them so that they're acting on the state that corresponds to the origin state. And then that gives us now this final result. So I'm a little bit going quickly over this. There are some technical things that you have to get into. This is the weeds that I mentioned that I'm not quite going into in great detail. If you do want the details, we have a paper that covers it and goes over all those great details. You have to actually think about this in some limiting factor with an infinitesimal that you translate along the z-axis so that those statements that cosine theta acting on the state is equal to 1 and so forth hold rigorously. Okay, so then what we get is our final form, that the state x, y, z in position space is e to the minus I phi over h lz, e to the minus I theta over h ly, minus I r over h pr minus I h over r hat, the whole thing acting on the state at the origin. And this is the way we write the translation operator in spherical coordinates when it acts on the state at the origin. Now, this term at the end looks like it's not unitary because PR is a Hermitian operator, but this other term, I h bar over r hat, is not Hermitian. So it appears as if that term is not unitary, but indeed it must be unitary because it produces the correct translation operator. So that is a red herring. It really is that this final expression is unitary. It's because of those simplifications we put in with regards to what happens with cosine theta hat and sine theta hat that make it appear as if it might not be unitary. But indeed, it's going to turn out that it is. And indeed, that is exactly the right quantum correction we need to put in to properly do the spherical translation operator. Okay, that brings us to the end of Lecture 9.